So today we are going to go over the normal fault assignment, which hopefully everyone has turned in. And then we're going to be starting our main mapping assignments. So hopefully you all got an email from me an hour or so ago saying what your assignment was. And then so after we talk about go over the normal fault homework, then we'll spend the rest of the class introducing these main assignments, which will then guide our work for the rest of the semester. So Rich, would you like to take it away?
You're muted, Rich.
Sorry. Yeah. Come up. Okay, great. Good morning, everybody. Yeah, so I wanted to go over the normal faulting assignment a little bit here. And I did look at, I'm about halfway through all your questions from the normal fault reading. And so my plan with that is just to write responses to your questions and then email them back to you. And if you have further questions, you can get a hold of me and we can talk about it. But there was, I've seen a lot of pretty interesting questions so far. And one that kind of keeps coming up is how to recognize oblique deformation along normal faults. And the answer is it's really tough. And generally normal faults are slipping at, most normal faults that I'm aware of in the world are slipping at a rate that's pretty slow. And the oblique sense of motion is going to be pretty small. And so it's often not really preserved very well. There's places, and I'll show an example along where we were working for the normal fault assignment where you can see some right lateral deformation, but that's kind of in an area that has sort of debris chutes related to the immediately post last glaciation. So the landforms are a little bit older and they do preserve it in a few spots. But the chapter mentions piercing points of river terraces and stuff like that. And that's where you can look for it, but it's very rarely preserved along normal faults. So I just wanted to start out by saying that I know mapping normal faults, well, it can be really easy where you have a really nice, sharp range front trace, but it can also be really difficult because as we've seen, there's steps in the fault trace, there's bends, there's places where it bends and becomes distributed. There's also secondary subsidiary faults in the footwall, like along the bedrock, along the range front, which generally have smaller scarps than the main scarp, and so they're not preserved very well. Also, it can be really wide deformation in the hanging wall with a bunch of faults, quartz and gravels and stuff, but these can also be really small and hard to recognize in the landscape sometimes, and they can be distributed over several kilometers. So there's challenges in mapping normal faults. So when we use the indicators that we've been talking about, you can kind of get a pretty good idea. And so I'm really interested to see what interpretations you came up with on this data set, but I'll go through and show sort of a recent geologic map that was published 2 years ago that I helped in mapping. And I'll just compare that to the LiDAR and point out some of the various features that I use to map the fault trace. So again, here's this picture of the basin of range with the Walker Lane in pink. Now I'll zoom into where we were working here in a second, but just keep in mind that we have a massive major plate boundary right lateral system just moving to the northwest, right along our western margin in Reno. And the fault that we were looking at, Carson King normal fault and the general fault to the south of it, are basically were originally basin of range extensional structures, and now they're being somewhat overprinted by this right lateral stress regime that's coming through the Walker Lane, which takes about 10 to 15% of the relative Pacific North American plate shear is accommodated along faults in the Walker Lane. So I just wanted to put up this map and give me a second. Let me turn the lights down in the front here. You can see. So I wanted to put this map up here. Here's Lake Tahoe, just right to the west of Reno. We were working along a system of faults right here. You can see my cursor. The Genoa fault is pretty north striking, and then it's distributed into a couple northeast trending faults, continues to the north, and then becomes what's labeled here as WVF, the Washoe Valley Fault, which is really the Carson Steam Drain Fault, and where we were working close to where the yellow dot first stop 3 is, which is from a field trip. But you can see this comes up here and then becomes really distributed again to the north. So along strike to the fault we were working on, I showed these pictures before, but it's worth noting again, is the Genoa fault, one of the more active faults in the Western Basin of Range. The fault's really evident along the base of the cliff here with the scarp and triangular facets. Wine glass canyons as well. Picture on the right shows sort of the same thing, fault running along the base of the slope here. So the oversteep and slopes, they're kind of shadowed in the sunlight in this photo, are indicative of active deformation. Some more pictures of the Genoa fault. Here's the fault plane exposed in the quarry at the base of the slope. So there's slicken sides on here that are normal. But there's also some slicken sides that are slightly oblique. So there is some oblique motion along this, but it's dominantly normal displacement causing this massive 1,500 meters of vertical relief on the range front. And there's actually about 500 to 1,000 meters of space and fill. So you got a lot of displacement along this. So here's the fault that we were working on, just some field photographs. To the south here, here's the range front right here in Washoe Valley. And then to the north, this is Mount Rose, and it's called Slide Mountain. There's a bunch of massive avalanches that have come off here. Many have been generated by earthquakes in the past. There's actually Native American legends from the last earthquake was about 500 years ago, and there was a massive free flow that occurred during that earthquake. But there's a bunch of debris chutes, and they're faulted to various levels, and we'll show or various amounts, and I'll show some pictures of that, or well, some LiDAR images of that maybe you noticed when you were doing the mapping. So anyway, this is Slide Mountain, and then you'll notice that the range front comes up here along my cursor, and then there's some low hills here that don't have really prominent geomorphology for active displacement, but as I'll show, it is there. And then our mapping went out to the north here on the Mount Rose scan. There's just a Google Earth imagery with Lake Tahoe and the faults here. So in orange here on the right side of the Sierras is the Genoa fault. Coming up in this little lake is Washoe Lake. And the faults we were mapping go right along the western side of Washoe Valley. And again, you can see there's a trace along the range front here. There's another trace up in the mountainside, and then this broadly distributed zone of faults up here. These faults are from the USGS Quaternary Fault and Fold database. This is just zooming in a little bit closer where the range front, where the faults are not plotted here. The range front shows up pretty nicely on the west side of Washoe Valley. So when we're mapping these things, we do try to hone in on the range front first, just to see if we can find the fault there, and then follow it and trace it as far as we can. And then when it disappears, then you have to make some judgments as to how the fault may bend through an area. So if you notice on here, on the right side, this orange fault along the western side of the valley comes up and kind of gets into a zone where you don't see any faults mapped, and then this big distributed zone to the north. But somehow it's getting through there. And the original mappers who put this together didn't map it through here. It's complicated, and I'm sure you found complications in there when you were trying to map it yourself. So here's the LiDAR imagery that we were mapping on, and interpretation in the middle, and then the final geologic map on the right. But again, and I'll zoom in on a few spots, but the range front trace is pretty prominent through here, maybe a little step here. But then this is this sort of promontory of bedrock that doesn't have a lot of vertical relief and doesn't have triangular facets and that sort of thing. But there are fault traces going through there as I've interpreted here. And I'll zoom in a little bit and we can talk about that in a second. But this is just sort of an overview of the whole homework assignment area. So uninterpreted on the left and interpreted on the right. The yellow arrows are pointing to geomorphic features. So down here at the bottom left, this arrow, we have sort of an offset quaternary landform. There's a nice scarp going across this quaternary landform. There's also cutting across, these are sort of debris lobes from debris avalanches that I mentioned coming off of Slide Mountain. There's scarps of various heights coming across those surfaces. Maybe some wine glass canyon here a little bit, but mainly just a kind of oversteepened range front. And then if you look further up into the mountain range, there's another scarp that runs along these yellow arrows here where there's sort of a little intermontane valley. I'll show a photo of it in a minute from up above, but there's scarps cutting across in this sort of curvilinear fashion of west of the main fault zone. So here's the same area with the geologic map on it. All the browns and oranges are debris avalanche deposits coming down, and then the faults are mapped in black, cutting across. And so these debris avalanches have various amounts of offset, some up to 60 meters and some down to about 5 to 10 meters. So some of these slides are older and have been around through several earthquakes, and some of them are younger and may have only been displaced by 1 or 2 earthquakes. And then there's a bunch of landforms up here, different, these are, the blues are glacial outwash deposits. So the ice cap was on the top of the Sierras, and basically ice melt was coming down these drainages and causing these sort of, they're not really fans, but they're sort of outwash fans, I guess. They're not really alluvial fans, but those are the blues. And so there's a couple little scarps cutting across the orange deposits here on the right side, and right along my cursor here, and they can be seen in the LiDAR, this little shadow right there. So we see a range, an oversteepened range front trace, and then also a little trace that's outboard at the range front or east of it. So I've oriented this, sorry, I forgot to mention, to north is to the right. So I've done this a couple times in the last lecture too. It kind of helps be looking at like perpendicular to the fault. So I sometimes rotate it to see it a little easier. So these are what some of these features look like in the field. So here's a offset quaternary deposit. So this is about a 2-meter scarp right here in the upper left photo. And then the lower 2 photos here show sort of this, on the photo on the right, this really steep slope coming down, but how it gets steeper right towards the base. So that's that over steepened slope that I was mentioning. And then this is a sort of a bouldery sort of outwash deposit with this kind of maybe a 5-meter scarp. Okay. So fault's running right along here. So that's the biggest part in the field. So here's looking a little bit to the south. There's an area where the range front trace again is pretty prominent coming through here. So there's also this fan here. There's actually 2 scarps, one isolating the fan across the front and one cutting sort of in the middle of it. And the profile tool, which I wanted you guys to practice using, is a good way to see that. So if you run a profile down that surface, you see that the upper scarp is about 4 meters and the lower one is about 7 meters. So the GIRs we're talking about, you may not see them everywhere, but it's common to see a lot of offset quaternary deposits. So I'll probably use that one a lot. Oversteepened slopes and scarps are kind of the most common ones that you will see along this particular fault anyway. So here's the geologic map of that, just showing the orange fan with a scarp cutting across the middle part of it, and fault map in the front of it. And so the nomenclature for fault confidence is a little different than what we're using here in the field for these state geologic maps, but you'll note that there's some lineaments that have question marks. And then this is dotted in front of this alluvial unit just because the younger ruptures was interpreted to be the one further to the west, and this is interpreted to be sort of buried by colluvium. So that's sort of a mapping nomenclature thing that the state mapping agency makes us do. But you can map that as whatever confidence you feel it's a fault. You can map it as a fault line. This is what that looks like in the field. So this photograph is just looking right back at this lower scarp here. And it's kind of behind the barn here. This yellow surface correlates with the yellow surface up here. So that's the scarp there, taller than the barn there. 7 meters on the profile. Then moving up to the north, we talk about horsts and grabens. There was a couple questions in the reading about horsts and grabens, and sort of, you know, they're formed by opposing scarps or faults with opposing dips, and they occur at different scales. So they occur at the mountain range scale, so horsts and grabens across the basin and range. We have mountains and valleys, but they also occur on sort of the local scale here. So this is the uninterpreted LiDAR on the left and the interpreted LiDAR on the right, with this red line of where I noted scarps. But you know, you generated a couple different hill shades of one coming, the lights coming from the east, and one the lights coming from the west, and you kind of compare the two. But in this case, the white slopes are facing to the west, and the darker slopes are facing to the east. So there's a series of these scarps in here. Some are facing the same direction, and some are opposite facing. So you create these little basins along the fault shape. And so they're kind of small, but they're pretty prominent. You can see, you can label them as scarps, you can label them as grabens. But then when you go to the south, that bedrock promontory I was talking about, that doesn't have a lot of geomorphology, when you look closely, like down in this lower right portion of the photograph, there's a series of these sort of west-facing scarps here, and they're bound by a really subtle sort of east-facing scarp. So similar sort of horst and graben situation going on here, and those are interpreted to be active fault structures as well. And then you have to really tease your mind to figure out how to get faults through some of these other areas. But there are a few lineaments and things. These dark shadows here in the middle, facing to the east. There's sort of there's just lineations really that correlate with topographic change that's along strike that projects into these horst and graben structures to the north. So I'm interested to see if anybody picked out some of these. That they're in there. They're very subtle and difficult to pick up. But some of the more prominent ones are pretty obvious, sort of these sub-parallel traces that are along strike of the main fault. Here's just the geologic map showing that. So the blue again is an outwash band from the last glacial maximum. So it dates probably around 15,000 years or so. The orange is a very old fan surface that has some of these horst and grabens on it. And then the orange is bedrock. So this is Miocene volcanic rock, and the green would be the granitic rocks that make up the footwall, the main footwall of the main fault. Yeah, I see a hand. Go ahead.
Yeah, I was just curious. I guess I got confused as to like what's bedrock and what's not bedrock, and so I didn't really map any bedrock, but I explained that in my project. I guess, like, how do you tell it's bedrock is my question.
Yeah, that's a good question, and that's okay. I mean, we didn't really ask to have all the different units, you know, sort of differentiated. But you can and like, deposits are usually smoother, flatter, geomorphic deposits. I mean, this is a big mapping effort to map the geology that I'm showing as examples. It took a lot of field time and stuff, but they're generally, have gentle slopes towards the valley. They're flatter. They don't have, bedrock is just more chaotic kind of in its eroding pattern. And, you see a big range front, probably bedrock, but some of these lower bedrock hills, it's a little bit more difficult to determine that. But if you look right up here, there's this sort of blue strip coming down this drainage channel. And then it sort of has a mouth here that opens up into this orange deposit. And so you can see that in the LiDAR where there's this steep canyon coming down. And then right about where my cursor is, sort of the mouth of the canyon. And so below that point, it's a little smoother and flatter. Okay. He's right here. Yeah, and so the question from the class is that some of these traces in the southeast were mapped as quaternary, and how this map shows it is actually bedrock and with some quaternary sand below, and that's okay if you observe it that way. Sometimes it takes fieldwork to really clarify that. In this particular area, it's volcanic bedrock, and there is a little bit of lag gravel on top of some of these little horse blocks, but you may not know that just by looking at the LiDAR itself. Another question, I see a hand.
It was just to jump on your idea. So I was wondering if we could also use the base map, like the satellite imagery base map, to identify bedrock. Is that fair?
You can.
Yeah, okay.
Sure, yeah. Sometimes it comes up with different colors, and sometimes when there's trees, it makes it tough. But different bedrock create different soils, and the ground swirls bring the soils to the surface. And so the satellite image, you can see sort of different tones and different colors that may be different than a quaternary deposit. So you might see that contrast, and then in your mind's eye, you can think about it, one side being quaternary, one side being bedrock. So good question.
On that, Rich, too, for like the base map in QGIS, you don't want to use that one, at least, because it will show remnants of the rupture that we were studying. So if you toggle it, the Google imagery is the most recent one, but using base map imagery from before the earthquake, like on Google Earth, if you wanted to toggle back and forth or georeference it too, you can do that. But if you use the base map,
Yeah, thanks for mentioning that. We don't want to use the Google Earth imagery with our pre-rupture mapping projects that we're going to be getting into soon. But in everyday mapping, when you're out there mapping, going back and forth between as many different base maps as you can come up with is generally helpful. I like to use black and white aerial photographs, color aerial photographs, just in stereoscope, old school style, and then LiDAR, various CEMs, and various satellite imagery. They all provide a little different perspective, and so just having a bunch of them in there sort of helps in your map. Okay. So here's the Horst and Graben zone in the upper part. We were just talking about this area in the last slide, but the profile tool shows these sort of west-facing scarps, east-facing scarps, and sort of some stacked grabens in the middle. So generally, the slope of this band, was originally kind of gently coming down from upper left to lower right, and it's just been dismembered a little bit by faulting. Same thing a little bit further south in these lineaments we were just talking about, except they're a little bit more rounded and they're larger. So the larger amount of displacement just suggests it's an older deposit. And if it's not a deposit, it's in bedrock, but it's showing a similar process of graben formation along strike. And yeah, again, these sort of graben features can be widely distributed over several kilometers. Yeah, good question, class.
Yeah, so when you're looking at a structure like this, to differentiate between like a traditional host and graben and looking at the other side, like half graben,
Yeah.
is there any way to do it other than just like looking for a complementary structure and not finding one?
Now you just have to look.
Okay.
So the question in class is, how do you know if it's a horse and graben structure, whether there's a structure bounding on one side or not? So basically, you just have to keep mapping and keep looking to see if you can identify a structure on the other side. Because you can still have distributed deformation on the hanging wall and not have a bounding graben fault on the other side. Although you can have that also. That's either one.
Also on the bottom one, how do we measure the offset?
Right here. Okay, so the question in class was about the measuring the offset of these scarps. And I think I have a slide at the end that shows it, but you have to sort of project the slopes. It's harder when it's eroded. The younger scarps, when you can actually match the slopes on both sides, it's easier to actually get a good measurement of the scarp height. Is definitely harder when they're all eroded. So in this case, I'd probably just take the upper elevation to the lower elevation, something like that, for a maximum. But there is probably some colluvium filling in there as well. So this is what the horse and grabens look like. If I go back one, it's a region right up here that's been pretty heavily developed with houses, but they were smart and they knew that there were faults there, so they left them out of some of the development tracks. So here's a east-facing scarp on the road. It's just paved right across the graben. Here's a house that's sitting on top of a scarp right here. This is an east-facing scarp. This is kind of like looking on the upper right, looking along strike, where there's a house on the upper part and some sort of structure in the graben. And these are active faults, right? With pretty recent, latest Holocene and almost immediately prehistoric ruptures. And then the photo on the bottom here is these sort of larger. So what we're looking at is the fault is running from left to right across the photo, and this larger scarp feature in the older bedrock / old alluvium surface. Question is this a gas container? Would it be safe to be next to an active fault? The answer is yes, it's a gas container, and safe along an active fault. Probably not during an earthquake, but it's there. Hopefully they have an automatic shut-off valve or something. But anyway, that's what those look like in the field. So if you calibrate your eyes again to what these sort of opposing scarps are like, and in the field, if you know what you're looking for and you have the LiDAR and your map in front of you, yeah, okay. But if you're just driving around the neighborhood to grandma's house, it might be pretty subtle to recognize these things. Okay, and I think the final example, how am I doing on time? Okay, almost done here. Is this fault trace that's up in the mountain range. And so so these are oriented north-south, and the range front trace would be off the images to the right side, to the east. And so this is this trace along the yellow arrows, and you kind of lose it in some places. It's not completely continuous, but it is pretty prominent, and it just sort of makes its way along here. There's bedrock here, bedrock, and I'll show a geologic map I think in a second. But coming down this massive drainage here, there's some moraine and some glacial outwash. And you may not know that just looking at this, but they're a little bit smoother, and they have sort of this downstream fabric to them. But it's mostly in the bedrock. And this is how that was mapped, where there's some glacial deposits in this little intermontane valley that follows this trace. It does cut, it's in black right here, it cuts across the bedrock, but it does cut across some moraine through here. And again, the green is the granite and the orange is the tertiary volcanic rock. This is what it looks like from a drone, just looking at the scarp, looking to the west. So this would be the road that goes up to the Mount Rose Ski Resort. And the interesting thing here is that these gullies, I mentioned this at the beginning of the lecture, cut across this pretty massive scarp. This scarp is actually like 20 meters high or so. And there's a subtle hint of right lateral offset with some of these gullies. So that might be where some of the lateral deformation of the Walker Lane is coming through. But it hasn't really been characterized as to how much. And this is that's the road that goes up to the Mount Rose Ski Resort. Mount Rose Highway would be up behind it a little bit. Yeah, I see a question.
Yeah, so
Mo?
there is like a steep, like a mountain with a steep slope on the western side of the fault, and I've marked that as being a fault because these two high reflectivity mountains, and
These two right here, yeah.
Yeah, and this thing was like quite continuous. It was going on for like, I would say, a kilometer or so.
Yep.
But then I was confused because it was also surrounded by anthropogenic activity. So I was wondering if that was natural or not. And also, like, since it was normal faulting and that looks a bit more like a reverse faulting element, I was kind of confused by it. So I was wondering if it was related to faulting or not.
Well, the high topography is definitely probably related to displacement along this fault, and there could be a fault on this side. I'm not sure, but yeah, we can look at the geologic map, and there's quite a bit of glacial activity here. These are like moraines and stuff. These circular ends are where the ice was sitting for a while, perched up there on top. I'll go back to the geologic map. So there's ice here, and it looks like there was a fault interpreted there, okay. With some question marks. But the highest part of the topography, you could consider it somewhat of a horse between two normal faults here. And remember, Lake Tahoe has several normal faults. The map I showed at the beginning, I can show it again at the end. But it's a series of stepping normal faults, and so it's quite possible that this is active as well and just helping to preserve this high topography.
Okay, because I was surprised that normal faulting would create high elevation features, but if you say it's possible.
If it's a horse, if it's dipping off to the west here and dipping off to the east there, it's sort of oppositely facing normal fault. So you just that high.
Okay, I see. Great, thanks.
Is it possible that the block there is tilted as well along that fault, creating some more topography? Because it looks like one of those sides is a lot steeper than the other side. But I guess it looks like that there was a granite, so maybe it's not a planar block there.
I mean, it's quite possible that one side is more active than the other side. You're generating more steeper topography on one side versus the other.
Okay, cool, thank you.
So anyway, this is a pretty amazing photo. So there is some right lateral shear that you can pick out in here. It's pretty subtle, but again, like what I mentioned in the beginning, piercing lines are really tough in this sort of environment. So this photo is right in here. There's the road above. Or it could be right in here. So the next thing I'm going to talk about is the scarp, the real prominent scarp that cuts across the moraines here. Okay, before I get into that, here's standing up on the road on the top, looking to the south along the Washoe Valley Fault or the Carson Kings Range Fault. So you can see the range front here along the valley margin, and then it kind of disappears from view below this slope here. But here's this intermontane valley that's pretty straight coming down below Mount Rose with this sort of secondary trait in the footwall block. So I've drawn a couple profiles here, and I asked you to sort of pick somewhere and try to estimate the age. So you remember that slip rate times recurrence is going to equal displacement. That's the sort of relationship we use a lot, and oftentimes we just have two of the parameters, and we try to play games with the equation to try to figure out how old a surface is, or we might try to figure out what the slip rate is if we know the other parameters. But so anyway, in this case, you guys could use the profile tool to estimate the height. And so is I was asking how you estimate the height, and basically on this upper one, it's just a projection of this slope, and then a projection of this slope, and then measured in the middle. We measure it in the middle of the scarp because there's some erosion and deposition of colluvium at the base of the scarp, and some sort of downgrading of the slope on the upper part of the scarp. So we try to measure it in the middle of the scarp based on a projection. But for the homework, if you just took like the height from there to there, that's fine. And so I picked two places where there was a 16-meter scarp here and a 37-meter scarp here. And if I plug in the slip rate that I gave you, 0.4 millimeters per year, comes up to about 40,000 years old and 92,000 years for the surface. If the slip rate's a little bit faster, this may come down to about 25,000 years, which maybe might be closer to the last glacial max time frame. So, the slip rate might not be totally accurate. It's based on just one or two studies that were pretty poorly constrained. But this just gives you an idea how you can use this sort of relationship to estimate ages or predict the amount of offset you might predict after a certain amount of recurrence time if you know the slip rate. And it's an equation we use a lot into it. So yeah, sorry I went a little bit over it. Any other questions? That's kind of, I'm really looking forward to seeing what you guys came up with. I know it's a challenge and it's a tough fault to make. Easy in some places, it's really hard. So it's great practice along a normal fault in a slightly oblique environment. Yeah. So.
Yeah, so there's one last scarp I wanted to check with you. It's a bit south of what we are seeing right now. So I don't know if you have a map where we can see that. Yeah, we can see it here. We can see it here a bit. So in the northwest corner, there is a scarp running diagonal to the map right now. Can you see it?
Right here, where my cursor is?
A bit higher. It's a bit more diagonal. Yeah, that.
Yeah.
Well,
yeah, I mean, you get into.
Yeah. But it continues further. Like if you have a bigger map of the region, we could see it like totally. My problem with that thing is that it was not running with the same strike as the rest of the scarps. But yeah, I was confused about it. Yeah.
And that's okay. I mean, you see that this trace here kind of bends off to strike a little bit more northeast. These are striking a little bit more northeast here, but there are a couple lineaments in the LiDAR here and coming up through here, and they sort of feed into this sort of major fault here. So, but yeah, I'm totally okay with faults mapped over here. If you observed anything, there's subtle lineations, there's scarps, features along strike, steep spatial slopes. There's several features that you can use to support mapping a fault there, and I put one lineament in right here, but they do sort of all project right into this major fault. So having a splayed system is okay.
Okay, great, thanks.
Okay, so when we're talking about defamation and how that changes from the south to the north, I was wondering, should we get like different concentration, like in our primary faults to the south? Are we getting a more concentrated faulting, and then it kind of is more distributed defamation to the north because of like the type of rock again, with that rock versus like more unconsolidated deposit, like how does that affect?
Yeah, so the question in class is why would it be more distributed to the north, and maybe could it be related to differences in the bedrock? And that's totally a valid argument. You have granite on basin fill in the south, and you have all this tertiary volcanic rock. So how the fault is coming to the surface may be manifest in a different way in different bedrock. That's totally true. Generally, I just wanted you guys to really recognize that it's a pretty straight, narrowly confined trace in the south and very distributed in the north. And common to see this happen along strike slip faults. Part of the reason here is that the dip of the fault here gets really low, and so it just becomes a fault. Yeah.
Sorry, are you able to tell the dip at all? Because I really am thinking that you're not able to tell the dip.
No, that's all right. You wouldn't be able to tell the dip from LiDAR. I just know that from geophysics. So, no, I didn't necessarily want you to know that the dip was,
Okay.
but just to think about what might be happening in a sort of a transtensional environment where you're having some lateral shear, some extension. You know, there has to be some sort of flip flop between the steeper dips and lower dips, and as these things are bending over. Anything else? I need to give Chelsea some time here. Sorry.
Yeah, let's move on. And maybe if you have questions,
Yeah, feel free to reach out to me with any
Next
other
time.
questions, and I'll get these graded and back to you, and we can have some more discussion about ophthalmology.
okay, thank you, Rich. So we're going to spend the rest of the class today introducing the main mapping assignments. And so all the work that we've done so far, learning how to map faults, learning the GIR, now is your chance to use these skills to make these high quality maps that PG&E is going to use essentially to figure out how to better, how to make their infrastructure crosses faults safer, as Steve Thompson told us about. So hopefully you all got an email or two from me this morning telling you what your assignment was. Is there anyone who did not receive an email? Excellent. Okay, so today I'm going to give a brief introduction overview to the assignments. Then we're going to go over the assignment handout, which is on the web page. And then I'll talk a little bit at the end about how to get the data that you're going to be using. Okay, hopefully you can now see my screen. Okay, so to give you an overview, there's several, 6 or so main assignments, and you've been assigned. Pretty much everyone is going to be doing the mapping repeatability assignment. Some of you will do it in this first half. Some of you will do it in the second half. And a few people who have seen all of these areas before are not going to be doing it. So for this assignment, you have a couple kilometers of fault length in different areas, including the Ridgecrest earthquake, Fukushima Hamadori in Japan, which is also sometimes called Iwaki, Bora Peak in Idaho, and then El Mayor Cubica in Mexico. And so for these, each section, there's a couple kilometers of fault length that we would like you to map using the GIR, using the fault shape file that we've given you. And our goal for this part of the assignment is to see how repeatable or how similar all of your maps are relative to each other. I believe Chris Medugo is going to also hire several consultants to do mapping in this area, so we can assess how similar they are, and as well as how well people with different amounts of experience can anticipate the future ruptures. Then a second assignment, the rest of these, just a few of the class will do, and everyone has one of them. This is going to be looking at the impact of adding a geologic map. And so we have Napa and El Mayor Cubica. And so for this assignment, you're going to assign to this, you're going to do mapping in the polygon shapefile that I sent you first with just different types of topography data sets. I want you to make a complete map, the GIR and the faults in the polygon. And then you're going to send that to me. Then once you do that, you're going to get a geologic or geomorphic map, as well as some background information on the area. And then we want you to can alter the map and the GIR features based on the new information that you have. So you're becoming, to some extent, experts. The question is, can experts map better than people with less information on the area? The next assignment is looking at data type and resolution. The question is, what type of data can help you do the best high quality map, and what information do you learn from different types of data? So we're looking, and this is San Andreas, Southern San Andreas Fault, 2 sets of examples in Salt Lake City in Utah, and then 1 in New Zealand. And so for the people that got those assignments, I gave you a list of different data sets to use. And it's really important that you map in that order. So essentially getting higher quality data, where I expect that you'll be able to see more. And again, after you do the map with each data type, then I want you to send me your previous map, and then you'll get the new data. So then we're building a few new pre-rupture maps, looking at the 2008 Nira earthquake in Kyrgyzstan, 2002 Denali earthquake in Alaska, the 1983 earthquake in Bora Peak. So yeah, this especially, it's important that you only use the pre-rupture data, actually also for the geologic map and the mapping repeatability. So I'll discuss how to get the data that you'll be using for those assignments. And then 2 people who indicated really strong excitement for statistics in the second semester, or second part of the assignment, will be looking at statistics. All right, are there any kind of big picture questions on these? No questions?
Just a comment, Chelsea, this is Rich, like, you know, for students, it sounds like it's a lot, but just like to recommend just going at it task by task. You know, each assignment has its own little, you know, set of instructions. So I know it sounds like a lot right here, but if you just do each one as it comes in a row, you know, you'll be doing the same kind of mapping that you've been doing. Just keep track of your data sets and everything else along the way. But and remember, we have a lot of time, and these are 2 main projects going on till the end of the semester, right? We'll have peer review sessions and things like that. So yeah, don't get intimidated. It's a lot of stuff, but it's all doable if you kind of take the time, you know, each week.
Yeah, so speaking of the calendar and the schedule, here we are, first day in March. We're going to be spending the rest of March on these first mapping assignments, and the report that I'll discuss in a few minutes, and all your mapping work will be due on March 31st. And so we have about 4 weeks, maybe a little bit longer, to do all of these mapping projects. Again, as Rich said, yeah, it's important to look at the schedule and really work hard on making weekly progress. And so discuss time management in a little bit, but again, so that you're making good progress every week and that you don't have everything to do last minute. So on that theme, like that everyone contribute about 5 hours of mapping each week. And this does not include the class time that you'll be getting for the mapping. And so sometime this week and then for each of these other weeks. So for example, if you're looking at the mapping repeatability, you have 5 areas and 4 weeks to do them. And so you should do each of those 5 in a little bit less than a week. If you're doing the impact of the geologic map, then you probably want to spend about 2 weeks doing the mapping before you get the geologic map, and then you'll have 2 weeks to revise your map with the new information from the geologic map. So on Thursday in 2 days, this is going to be a required office day. So we'll go over any material that we don't discuss today. And then the rest of that class is for you to ask us questions about how to get started. So for example, how to access data, any questions you have about what you're actually supposed to do, how the mapping is going to work. And so your homework for Thursday is to get started and make sure that you can take advantage of this opportunity of having at least me, Rachel, and probably Ramon here to ask any questions that you want to. And then, so then next week is the ASU break. And then following week is the UNR break. And so class will, official like lecture style class is going to be canceled both of these weeks. But you must take advantage of that extra time. You don't have to spend in class to do the mapping. And so to help you do that, when it's not your break, you must check in during the class time. And instructors will be here. So if you have any questions about the mapping, it's a great, it's sort of like free time to get your questions answered. And we're also going to be having private or semi-private meetings during these times with your instructors to get really detailed and personalized feedback on your mapping. And so on Thursday, we'll work on scheduling those. And then again, the reports will be due on March 31st.
So this is Rich. So for you and our students, I will not be here on the 3rd, this coming Thursday. Question from the chat, do we have class on the 22nd?
Yes. So McGill, do you have to, so it's really up to you, but at least one of those weeks you must check in. I'm not going to micromanage, but it's class time. You really should take advantage of it. And again, you'll have at least some of your instructors here to be able to just ask any questions too. So this is a really great opportunity to help you learn how to map better, probably not or waste less time figuring out how to access the data. So take advantage of these 2 weeks and be sure to make the progress for the mapping. Okay, are there any other questions? Okay, so on the web page, if you go down to today's schedule, you can find this information, which is the handout sheet. Just wanted to go over some of the major points. The first is that we expect you to spend about 5 hours a week mapping. There's 4 hours or 4 weeks for the project, so that's about 20 hours total. And this doesn't include the class time that you spend mapping. So for example, hopefully you start mapping at least by class on Thursday, but that doesn't count for this total 20 hours. Important part is that we plan to use your maps in subsequent analysis and very likely publication. And so students who complete this mapping, this assignment with care and professionalism will be invited to be co-authors. And we're preparing a publication based on the last class, and all the students, yes, completed the assignment with this care and professionalism. And so hopefully, yeah, you find this inclusion in the research production exciting. So what to include in your mapping project? At the beginning, we'd like you to at least do 2 hours of this morphology and or geomorphic or hybrid mapping. So pick an area and spend 2 hours doing this type of mapping. After those 2 hours, it's up to you if you find it beneficial or not. But in your report, we do want to see the work that you did from this initial several hours or 2 hours. Then you must use the geomorphic indicator ranking that you've been working on developing the skills for over the semester. And Rachel recently posted a new GIR file, which just includes a few more features, GIR features based on recommendations that we've received from you in this class. And then fault mapping, you're going to use the same shapefile that you've used for the past several assignments. So in this should include the faulting line work that you've been doing. You'll also be assigning a confidence ranking to the faults. Again, we want this to be based on your geologic intuition, and you can use that informed based on the geomorphic indicator ranking mapping that you've done. We expect your fault segments to be 1 kilometer or so, on the range of 500 meters to 1.5 kilometers is fine. And it's up to you exactly where you want to break those, have those breaks. But we expect that confidence ranking does represent some sort of averaging of the signal, as we discussed before. So 500 meters is definite, or so if your lengths are only 50 meters, it's definitely too fine, or 5 kilometers is too coarse. Primary or secondary, so you'll want to distinguish between faults that you perceive to be primary versus secondary. We'll discuss these types of faults in detail in the class right after the break. But you can see in this text some descriptions of when faults might be primary versus secondary. Are there any questions on that part?
As a quick note with like the confidence ranking and with the prior mapping, the areas that you guys are going to have are on average a lot smaller than the areas we've been giving you guys in previous assignments. So don't get overwhelmed thinking you have to like do all of this like hours of mapping, because it's going to be a lot smaller. So you guys are going to have more of an opportunity to make a more like high quality map and even coverage throughout the area. And then the same with like the kilometer segment, some areas won't be big enough for you to implement the hard and fast rule of the 1 kilometer. So that's when you're gonna want to rely more on the geologic intuition.
So I agree that the repeatability areas are smaller. But some of the other areas are going to be bigger, but that's why there's 5 weeks to, or 4 or 5 weeks to work on them.
One question. I'm in the field all of spring break, and am I expected to make up the 5 to 7 hours of mapping time that people would be doing during that time?
Ideally, yes. But if you want, we can chat offline. Or you can chat with Rich.
No, I would just say it's kind of considered homework, so yeah, this would be a little bit of maybe catch up before spring break or after spring break if you need to be away for field work and stuff like that. But we're hoping that we can put some of that time back either before spring break or after spring break, so that you have that 20 hours.
Okay, so after we get back from spring break, one of the important parts that we'll be doing for this assignment is a weekly progress checks. This will probably take place every Thursday. And in these, we're going to break up into breakup rooms. Each room will have several students, and instructors will rotate between the rooms. And it'll be your job to present to the other students in your room several slides based on your mapping progress. So where are you working, where's going well, and where do you have questions on? And the idea is that you get feedback. You guys hear me?
Now we can.
Okay, how long was
Did you
I?
hear the question from?
No.
No. Well, the question was just like, if people who take care and professionalism in the mapping will be invited to be part of this research project. But I guess if the mapping is not up to a certain standard, will maybe not used or something like that. And I think the answer is that no, if you take the care and professionalism to do it,
Well,
regardless of the quality.
So we
Well, that
expect,
was the question, that if they don't complete the quality review, think there is any cooperation.
Because we're trying to characterize variability.
Okay.
so if, can you guys hear me?
Is that okay?
Now we can.
If you complete if you put in the time, you take advantage of the ways to get help, and you use what you've done, what you've learned in the semester, I have full confidence that your map will be of high enough quality.
I think Ethan's question was, regardless of the quality, is the data going to be used in the publication?
Unless you tell us you really don't want it to be, yes. In the publication we're doing right now, we have removed everyone's name from exactly their map, so that information is no longer there. But so for example, one of the questions we have is, how repeatable is mapping by different people? And so for that, it's really important that we get as much data as possible. And so we expect that the maps are going to be different. And it's really important for us to be able to capture those differences and understand how different people perceive the landscape and how that impacts their map.
And even if you are going to be a co-author, and you could correct me if I'm wrong, Chelsea, even if the maps are high quality or not, regardless, if you are a co-author, all of the data that we publish and all the subsequent analysis is going to be de-identified regardless.
Can you release a rubric for each mapping assignment type before we start this, so that we know?
We're getting down there. It is going to
Okay,
be
cool.
fairly similar though. but we'll show you. So on the website, you'll find a code of conduct, which is right here. Essentially going through how we expect you to be professional during these check-in times. And so the idea is that you participate and that you give appropriate and constructive feedback to your classmates. And if there's any questions about these check-ins, then please get in touch with one of the instructors. And you can also find this on the webpage. Okay, so now I'm going to go over a few guidelines for the project. So in the emails that you received today, I indicated, at least for many of the projects, the data that you should use for those mapping assignments. And so it's really important that you do not consult any post-earthquake topography or imagery. So this includes the base map in GIS programs. So for the mapping repeatability, sent you the link to all of those data sets. And then for the other assignments, I'll show you today, or maybe next time, how to get the data that you need for the mapping. Mara, what is your question?
You probably should turn off your video because you're really choppy.
Okay. Similarly, it's important that you do not research the earthquake. We want essentially design this project because we want people who don't have experience about these earthquakes to do the pre-rupture mapping. But if you really think there's some information that you need to know, get in touch with us before you look up any extra information. We can evaluate if it would be helpful to you. You must work individually. So you can discuss the mapping in class and in office hours, but otherwise it's important that you work alone. And again, we expect that the mapping to vary by individual. And a lot of these assignments are designed to capture those differences. So yeah, please work individually and help us to reach our research goals. Some of the data sets that you've received are publicly available. So this includes georeferenced Google Earth imagery. But other data sets are shared with us by colleagues. These data sets haven't been published. And so it's really important that you do not share this data outside of the class. So for example, one of those data sets for a peak. And so we trust that you'll use it only for the class and then you'll delete the data after the class. For those projects where you're looking at data quality or the impact of a geologic map, once you've finished mapping with one of the data sets, then it's important that you send me all of your mapping work and that then later you don't go back and edit your old files. And this is true even if the newer data helps you to see something that in retrospect was in the earlier data. Point of how we've designed the assignments is that we want to see what are the features that you can observe with each of the data sets. So send me the all your mapping work in a zip file when you're done with that data set. So you're going to be working on a report, and this includes what we want you to include in your report. So these reports for the first assignment will be due on March 31st. So here's just an outline. Everyone is going to write a paragraph about the type that they used, the type of data that they used, and the scale that they did their mapping at. And then we'd like one paragraph describing how you placed the confidence ranking on the faults. And then for each of these other projects, we want you to address these specific questions, but everyone will write, we'll have 3 figures and each with half of a page of text. And all maps should have a scale bar, legend, north arrow, and a caption. Are there any questions so far? So we've have some list of YouTube videos that may be helpful, how to save imagery from Google Earth, and I'll go over this next time. Save and submit shapefiles, which I believe you're all experts at now. And then Rachel just made this video about how to make this map with all of these features that you need in QGIS. So here is that rubric that will be applied to all of the assignments. And it's essentially looking at, are you implementing the skills that you've learned so far in the course to do the fault mapping? So I don't really want to go over each point, but if you have questions, you can feel free to ask. So we're actually very close to the end of time. So at the beginning of next class, I will show how to get data, or show you again how to get data from Open Topography, and then how to save high quality pre-rupture imagery from Google Earth. Are there any questions?
We're good on this side.
So before next class, I suggest that you look over the assignment that you've been given. If you have mapping repeatability, you can definitely go ahead and get started, because we've given you all those, we've given you the data sets to use, and we don't want you to look for other data sets. If you have a different area, then for some of those, I've given you the first data set to use, which you can go ahead and get started on, or you're looking at SRTM topography as the first data set for mapping, which you'll get from Open Topography. So you can see if you can go to Open Topography, download the SRTM topography, and then make a hillshade and start mapping from there. Are there any questions?
As a quick note too, at the end of the new GIR document, I put instructions on how to add a feature of your own. As some of you mentioned, there's like certain things that you see that aren't necessarily listed in the GIR. So there's a step-by-step like walkthrough at the end of the new GIR table that will show you how to add one of your own if you like.
I guess the only thing I was gonna say, so those of you who have the repeatability, wrote it down, but I don't think I sent it to you. If you told me you already experienced or you've done work in some area, then do not do the repeatability assignment there. And so a few of you I've given a different assignment to, or just actually removed you from the repeatability. So yeah, if you have questions about that, then let me know.
Okay, well, thanks, everybody.
Are there any questions?
Anything else come up in the chat, so.